Good morning. My name is Béla Nagy, and I'm presenting my work with Dawn Farmer and Jessica Transik, funded by the National Science Foundation at the Santa Fe Institute, based on data from the new performance curve database created by our student volunteers. We asked a very simple question. Is technological progress predictable? What do you think? When I ask others, some people immediately mention Moore's law, which is not surprising. Moore has become such a poster boy for predictability. I mean, literally. This is a 2005 40th anniversary of Gordon Moore's famous 1965 prediction that the number of transistors on a chip will double every year. However, that had to be revised later for a doubling time that's 2 years. You can see this for yourself. If you put a ruler on this green line, when you were living back in the 60s, you'd be way off in your projections. In fact, by 2009, you'd be off the chart, which is a pretty serious error, especially on a logarithmic scale. Curiously, no one else seemed bothered by this during the celebrations in 2005. Then I remembered my advisor's wise words back in grad school, who said that it doesn't really matter if something is wrong, because the real question is, can it be saved? So I set out on a quest to see if I can save the predictive power of Moore's law. I contacted Dr. Moore, who sent me his data, conveniently starting right around this breaking point so that I could ignore these early data points. And that allowed me to carry out a more rigorous analysis in an extended framework, not only for the memory chips and the transistors shown here, but including other unrelated technologies as well. And that's what this talk is about. In other words, this talk is about performance curves that can be seen as extending Moore's law for integrated circuits in 3 steps. First, there have been many attempts for a generalized Moore's law for computing in general. And what we see there is plotting some techno-juju as a function of time. But we can also define Moore's functional form for technology in general, using cost or price as a function of time. Finally, we can also consider other functional forms for technology in general, cost or price as a function of other variables. So first, let's see some examples of the generalizations of the first kind. One of my favorites is this chart of MIPS, million instructions per second, from the earliest computing machines in the 19th century to the latest supercomputers by Koch and McGee, who claim that this is exponential growth. But if this was really an exponential, then it should look like a straight line on a logarithmic plot. Does this look like a straight line to you? Or do you see a break in the trend? Well, that's what Nordhaus sees using a similar metric for computing power, saying that there was a major break in the trend around World War II, which is, of course, not very satisfying if you want to extrapolate, since how do you know there isn't another break lurking just around the corner? This is Cohen-Magee again. MIPS per US dollar. Is this a straight line? Ray Kurzweil doesn't think so. He sees another exponential on this logarithmic plot that he was showing us last night. And he's arguing for a so-called double exponential, where the exponent itself is an exponential. So, what do all of these graphs have in common? They plot some techno-juju as a function of time, sometimes ignoring some inconvenient early data points that don't fit a perceived trend, that is then projected to reach some mythical big juju in the future. Of course, this is a slide from 2007, so you might have seen that. We are arguing that this view is too restrictive, and we need a more general framework to understand predictability. Instead of some very specialized techno-juju, let's use cost or price. That's much more general, so that we can relate different technologies. That's how we compare apples and oranges, don't we? We put a price on them. Instead of relying only on time, take into account production volume too. And please don't use in-sample goodness of fit measures, such as R-squared, because the relevant criteria is out-of-sample prediction accuracy. And I'm going to show you what that means shortly. Finally, instead of just using one curve at a time, it's better to pool the evidence and analyze multiple curves at the same time. There have been a number of functional forms proposed in the literature. Wright preceded Moore by 3 decades. And there is more in Goddard, Sinclair et al., and most recently Nordhaus, using a variety of predictor variables. So let's look at some of these and see how well is cost or price predicted by these variables. Here, the most used formulation does not belong to Moore, who only uses time. That goes to Goddard, that goes to Wright, who in the 1930s observed that improvements seems to be a function of the total cumulative production. But that variable is the sum of the previous two. Production experience before the current year and the volume in the current year. So we tested those two, calling this one lagged right because of the 1-year lag, and this one Goddard, who argued that this was the only important variable. And the surprising bottom line of this analysis is that by keeping these two variables separate here, Sinclair is able to predict better than either Moore or Goddard, which is remarkable for 2 reasons. One, this functional form of Sinclair's is virtually unknown, only appearing in this 2000 paper, as far as I can tell. And the other reason is that by using 2 variables instead of 1, it should suffer from overfitting, like all the other 2-variable functional forms, such as Nordhaus. But you will see that's not true here. For example, let's see how good or bad Moore's functional form is on the data provided by Dr. Moore himself. Well, how do we evaluate that? Fit some regression line and calculate R squared? Of course not. You know that's wrong, because it tells you nothing about predictability. Instead, what we need to do is to pretend that we live in the 70s or 80s, and using only the data available up to that point in time, try to predict the future. This way, we can evaluate past forecasts with the benefit of hindsight. That's why this is also known as hindcasting instead of forecasting. So let's see how well does Moore's functional form predict transistor prices. Ironically, the answer is not very well. As we utilize more and more data points year by year, as indicated by these shades of gray, we can see that no matter where we start to predict future prices, Moore's functional form consistently underestimates them. Of course, this contradicts Moore's exponential presentation of his data, which is, by the way, really fun to watch on YouTube. But this is not exactly an exponential. And because of that, time is a lousy predictor. Are the other functional forms more accurate? With the exception of Nordhaus, which is all over the place, we can say yes. Incidentally, these are exactly the same ones that don't use time explicitly as a predictor variable. Only Moore and Nordhaus use time, and sure enough, they deviate the most from the data. Another way to visualize the difference between the predicted and the actual values is to plot the error as a function of the origin and the target year, sometimes after that origin. We can see that the error, plotted on this axis, rises from 0 at the sea level in blue, going through the topographical colors until it reaches the snow line at 1 order of magnitude. That is a factor of 10. But it doesn't stop there. The uncolored part of this mountain rises above 2 orders of magnitude, which is over a factor of 100. With all due respect to Dr. Moore, his functional form doesn't predict his transistor data very well. But who is the winner? On this particular data set, Goddard seems to be the most accurate. As you can see, there isn't even a mountain to speak of. It's mostly just green pasture. Sinclair is also close, with some trade-offs. And overall, if we take into account other technologies as well, Sinclair, in fact, is significantly better than both Moore and Goddard. Now, by taking a look at all the error mountains from the top, I'm going to show you all the hindcasting errors on just one page, including all the technologies used in this study. Are you ready for that? Okay, here we go. The first row is for the transistor data set that I've been talking about so far. The second is for DRAM, dynamic random access memory, and the third one is for hard disk drives, where we have price per bit These white lines, by the way, shouldn't be here. You can ignore them. That's just supposed to be all blue. And we have some other technologies, some chemicals, photovoltaics, and some other technologies where we had a unit price. And we compare the competing functional forms here. We compare them jointly on all these data sets. Now you might ask, how significant are the differences between these functional forms? That's not obvious at all just by looking at this data. Well, one way to evaluate that is to build an appropriate statistical model and to come up with some approximate p-values for the pairwise comparisons. And based on that, we can be pretty confident that Sinclair beats both Moore and Goddard, as indicated by these very low approximate p-values. However, for the other comparisons, there are still some large uncertainties that need to be resolved. And for that, we need more data. And the good news is that whatever technology you are working on, you can help us if you have historical data. All you need to do is to upload your data in any format at pcdb.santafe.edu. Thank you. Any questions?
Got it. We did, except no one took the stage. No. You got, okay, one question right there.
Moore's law is a self-fulfilling prophecy, which evidently is not fulfilling itself so well, according to your analysis, with hundreds of orders of magnitude of mistakes, potentially. It dictates a global lockstep of engineering efforts in order to make sure that it happens. So if it fails, it's not a failure of science, it's a failure of engineering, or resources may be dedicated to solving new problems. So how does your analysis help future engineering groups produce better solutions to their problems?
Well, many people have pointed out that Moore's law has been in operation before Moore observed it. So that means that the self-fulfilling prophecy has been discredited, because that's a hypothesis and it's not supported by data. For example, if you look at this paper by Cohen-McGee, you see that these exponential looking trends have been going on for more than a century. And Moore's law is not unique at all. This is just one example, this slide. If you look at his paper, you're going to see many more slides like this. This is another one, and it's not even unique to information technologies. For example, Cohen-McGee have another paper about energy technologies, and the surprising thing is that if you look at those trends, they look roughly exponential as well. It's just not as fast as in information technology, but we see the same underlying regularity.
All right. That's all we got time for.
All right.